Okay, we're going to cover a little over a page of the notes in section 5.1 on the natural log function differentiation, just to make sure that we have time to finish the entire section on Monday. So what's the motivation of doing this? Well, remember we had this indefinite integral formula. The integral of x to the n dx is x to the n plus 1 over n plus 1 plus c. Well, what was the problem with this formula? Notice if n is negative 1, then the integral of x to the minus 1 is x to the n plus 1 over n plus 1. Well, this term becomes 0, which makes the formula meaningless. So we assumed n could not be negative 1. So in practice, what does this mean? So as of right now, when we have the integral of x to the minus 1 power, or 1 over x, we don't know that antiderivative because it doesn't fit this formula. So that's what this section is all about, is figuring out what we're going to do about the integral, indefinite integral of 1 over x dx. Okay, so that's the first issue. We're going to define the natural log function, ln x, by the definite integral from 1 to x of 1 over t dt. Now this should look sort of familiar. This is the sort of expression we had when we were doing the second fundamental theorem of calculus. And so what is this going to be? For example, let's do this first example. Let's look at natural log of 3. So if x is 3, this natural log of 3 will be the integral from 1 to 3 of 1 over t dt, right? I'm plugging in 3 for x here, so I'll plug in 3 for x here. Well, the graph of 1 over t from 1 to 3, this is a continuous function from 1 to 3, so the function's integrable. So pictorially, what do we have here? So again, the graph of 1 over t, you have a branch in the first quadrant and a branch in the third. Since we're going from 1 to 3, we're only concerned about the branch in the first quadrant. And we're integrating that function 1 over t from 1 to 3. So this is the integral of this function. The function's on or above the x-axis. So all this is asking for is what's the area under that curve 1 over t from 1 to 3. Now, I mentioned in the notes you can use an integration feature on your calculator and actually compute this. Just to save time, I'm just going to tell you what it turns out to be if you do that. Okay. This turns out to be about 1.099. So the area under the curve 1 over t from 1 to 3 is about 1.099. Okay, let's look at b here. B says natural log of 10. Again, if we use the definition of natural log of 10, you put a 10 in for x. That's the integral from 1 to 10 of 1 over t dt. Now pictorially, what are we doing here? It's the same curve, 1 over t, and we're integrating from 1 to 10. Now think about how this integral is going to pair with the one we just did. This was the area under the curve 1 over t from 1 to 3. This is the area under the curve 1 over t from 1 to 10. So just from that observation, natural log of 10 should be bigger than natural log of 3. And so if you want to use the integration feature on the calculator, you can if you know how. And this turns out to be about 2.303, which we expected. The area of this is going to be larger than the area of that. Okay, the next one says C says do natural log of 1. Okay, let's do the exact same thing, natural log of 1. Again, the definition of natural log of x here, that's the integral from 1 to 1 of 1 over t dt. And you already know what the answer is, but again, pictorially, if we take the curve 1 over t, here's 1. Well, we're integrating from 1 to 1. The area under that curve, there's no width at all, so the area is 0. Or use the property we learned, the integral from a to a of a function is 0 as long as the function's defined at 1, which it is. So we knew this was going to be 0 even before we looked at the picture. Okay, and then lastly, part D says do natural log of 0.5. Okay, by the definition, natural log of 0.5 is the integral from 1 to 0.5 of 1 over t dt. Okay, now let's draw that picture. So here's my curve 1 over t. And here's 1. I've been using 1 as my boundary every single time, but notice instead of moving to the right like we did with 3 and 10, we're to the left of that at 0.5. now, what is this answer going to be? Notice that the upper value here, the upper limit, is smaller than the lower limit. So we have a property that says if you switch those endpoints, you're off by a minus sign. And so the integral from 0.5 to 1 is going to be this area, but the negative sign out front is going to be the negative of that area. So even though this area is not, even though my graph is not below the x-axis, the answer is negative because I'm integrating from, well, this is, from right to left, right? From a bigger number to a smaller number. So when you switch the endpoints, the answer is going to be negative. Yeah. Okay, and then if you again use the integration feature on the calculator, you'll get that area is about minus 0.693, and which is what we expected the answer to be negative, and it is. Okay. And I didn't state this before. We're assuming the domain of this function x is greater than 0 here, right? So we're assuming that x is positive. Because you don't want to put a negative value here, because if you put a negative value here, you're jumping over the vertical asymptote at 0 here. And we don't want to deal with that. Same with 0. If 0 is a vertical asymptote, we don't want area up to the vertical asymptote. Okay, so we have those values. It says sketch the graph. So based upon these few values we have, they want us to sketch the graph of natural log of x, of this function here. Let me make some room. Okay, so here we got natural log of 1 is 0. Okay. So now I have room to draw the graph. So we're plotting points for natural log of x. Again, the domain is positive, so we don't have any graph over here. Notice when x was 3, we got a log of 1.099. So at 3, we're just barely over 1. We did natural log of 1 turned out to be 0. And when I go up to 10, 4, 5, 6, 7, 8, 9, 10, natural log of 10 was just a little bit over 2. So when you come way out here to 10, you're just almost at 2.5. And then the other point we got at 1/2, natural log was about negative 0.7. So at 1/2, I'm down here. Now I hope you realize the further out we go this way, the larger the x is here, the bigger the area under the curve is going to be. That's what we saw when we did 3 and 10. So the graph is going to be increasing. Notice how slowly it increases though. Right? When we're at 3, we're at 1. When you're at 10, you just barely made it over 2. Right? Now what's going to happen here between 0 and 1? Suppose I change this 0.5 to 0.1 to 0.1. Now I'm going to be here at 0.1, so the area is bigger than it was when I did the 0.5, but notice the answer is going to be negative again, so it's going to be more negative. So the closer I get to 0, the more negative the area is going to be. So you actually wind up with a vertical asymptote here. And again, this was the graph you learned of natural log of x in pre-calculus. Now this isn't the definition you had in pre-calculus. You had a different definition, which in practice we will use. We're not really going to use this after this section. So there's your graph of natural log. Now what's the domain? The domain is positive x's. We assume that here. What's the range of this function? What are all the y values we hit? Well, you hit every y value going down to minus infinity, and you do hit every y value going up. It increases very, very slowly, but you do get every y value. It's all real numbers, yeah. So the range is all real numbers, or minus infinity to infinity. Where is this function increasing? So my function log y is increasing, not negative infinity. There's no graph here. It's increasing from 0 to infinity. All x values for where the function is defined were increasing. And notice the graph is concave down from 0 to infinity as well. So the function's increasing and concave down from 0 to infinity. And again, you didn't know about concavity in pre-calc, but you knew about this graph. So there's an example of a graph with a vertical asymptote at 0. Okay, now let's shift to the calculus part of this. let's come back to this definition of natural log of x and relate it to the very first thing I mentioned when we started this section. Okay, so natural log of x is defined to be this integral from 1 to x of 1 over t dt. Well, we learned how to use the second fundamental theorem of calculus to do a derivative of this sort of a function. So what's the derivative of natural log of x? Well, what the second fundamental theorem of calculus say, if you have a constant here and a plain old x here and a function here, how'd you take the derivative? You just plug the x in for the t. Okay, so using the second fundamental theorem of calculus, we get the derivative of natural log of x is 1 over x. Okay? And we're going to see in the next section what's the integral of 1 of x going to involve. It's going to involve a log x, right? The derivative of natural log of x is 1 over x, so the indefinite integral of 1 over x is going to involve natural log of x, which is what we were trying to do. Remember, we didn't know how to integrate 1 over x before this section. Okay, now what if you have the chain rule here? So what if I want to take the derivative of natural log of g of x, so stuff? Well, say the rule with x, the derivative of natural log of x is 1 over x. So the derivative of natural log of stuff is 1 over the stuff. And then chain rule always says multiply by the derivative of the stuff. So that's what goes in the blank in theorem 5.3. So that's just applying the chain rule. Okay, now let's look at this derivative formula here. One thing we don't like is the domain of natural log of x is x greater than 0, right? The domain of 1 over x is all real numbers except for 0. The domain of this function, 1 over x, is larger than the domain of the natural log of x. So even though you can plug a negative number here to get an answer, the negative number doesn't make sense here. So we don't like inconsistencies like that. But okay, let's draw the graph of natural log of x, right? And what's this, at x equals 1, we know not log crosses the x-axis, log of 1, natural log of 1 is 0. Now, what's the slope of the tangent line at x equals 1? Well, the derivative is 1 over x, so if I plug 1 in for x, you get the slope here. The slope of the tangent line at x equals 1 is 1. So there's a rough sketch of that. Okay? Now, what if we modify this? Let's look at the function. This is natural log of x. What if I look at the function y is the natural log of the absolute value of x? Now, I still can't plug in 0 because you'll be taking natural log of 0, which is undefined, right? You can't take log of 0. But now, with the absolute value bars around the x, I can take log of a negative number. For example, if I plug in negative 1 for x, absolute value of negative 1 is 1, and log of 1 is 0. Right? What if I plug in, 2? If I plug in 2, natural log of 2 is up here somewhere. What if I plug in negative 2? The natural log of the absolute value of negative 2 will be the same as the natural log of 2. So whatever number I got here for 2, I'm going to get the same value for negative 2 over here. So you see what's going to happen. The graph is going to do this on this side. And we have symmetry about the y-axis. Okay, so this is the graph of y as natural log absolute value of x. Now, we know the derivative on this side is 1 over x. What's happening over here? Well, if I sketch the tangent line here at negative 1, the slope of this line was 1. This line is going in the opposite direction. It doesn't have the same slope. Notice that all these slopes, because the function's increasing, all the slopes are going to be positive. Here on this side, the function's decreasing, so all the slopes are going to be negative. And in fact, because of symmetry, hopefully you can see the slope of that is going to be negative 1, the slope of that tangent line. And at 2, the slope of the tangent line here is 1/2, 1 over 2. And over here it'll be minus 1/2. Okay? So if I take the absolute value here, what's the derivative of the natural log of absolute value of x going to be? Well, if x is positive, you're still going to get 1 over x, right? When I plug in 2, I get 1/2. When I plug in 1, I get 1. You might be inclined to put absolute value bars here around the x. But what's the derivative? What's the slope of the tangent line at negative 1? If I plug negative 1 in for x, that'd be 1 over absolute value of negative 1 is 1, and the slope is not 1. In fact, the derivative formula stays exactly the same whether you have the absolute values around natural log the x or not. So this is the derivative of the natural log absolute value of x. It's still 1 over x. Okay, so the derivative of natural log of x is 1 over x, but you're only allowed to plug in positive numbers. Here, the derivative of natural log of natural log absolute value of x is also 1 over x, but here you can plug in negative values for x to get this side of that graph. And now what's the domain? The domain of this function is all real numbers except 0. The domain of this is all real numbers but 0. So that's why we did that, so we'd have a compatible domain and range here. Okay, so on the next page, I just mentioned that. So the derivative of natural log absolute value of x is 1 over x. Well, what would the chain rule say? What if I put absolute value around the stuff? So the derivative of natural log absolute value of x is 1 over x. The derivative of natural log absolute value of stuff is 1 over the stuff. Derivative of stuff. It's the same derivative formula with the chain rule, whether you have absolute values on the argument or not. Okay, so for practice, let's do a couple of derivatives here. So suppose f of x is natural log of 2x cubed minus 7, and it says find the derivative. So pause the video for a minute and see if you can compute the derivative on your own, and then I'll do it and we'll see if we get the same answer. Okay, so let's see what we get here. So this is chain rule. The derivative of log of stuff is 1 over the stuff times the derivative of the stuff. And if you want, you obviously can put the 6x squared in the numerator. Okay, so the next problem says f of x is natural log absolute value of sine of x to the 4th plus 3x cubed minus pi. So the first problem did not have absolute values in it. This one didn't, but hopefully you realize it's the same procedure. So again, pause the video and see if you can do this derivative, and then I will do it. We'll see if we get the same answer. Okay, so the absolute value doesn't change anything, right? Whether you have the absolute value around the x or not, the derivative is still 1 over x. But notice this is natural log absolute value of stuff. So the derivative of natural log absolute value of the stuff is 1 over the stuff times the derivative of the stuff. So this is a chain rule and a chain rule. So what's the derivative of sine of stuff? It's cosine of stuff, and I've run out of room, times the derivative of that stuff. So that's 4x cubed plus 9x squared. Pi is a constant, so the derivative is 0. So let me check my work here. The derivative of natural log absolute value of stuff is 1 over the stuff times the derivative of the stuff. The derivative of sine of the new stuff is cosine of new stuff times the derivative of the new stuff. And there we go. So there's the derivative of that. Okay. Now let me jump ahead. Go to the next page of the notes, the last page. We'll come back to the properties of logs on Monday. So remember when I was using this definition of natural log of x, and I drew some pictures here. Let me draw this curve again. 1 over t. So y is 1 over t. So when we plugged in, when we took natural log of 1, remember natural log of 1 was 0, because at 1, the area under the curve was 0, right? And then we plugged in, what was it? Natural log of 3. So when we did natural log of 3, the area turned out to be about 1.09, the area here. Okay? So notice when we take natural log of 1, we get 0. When we took natural log of 3, we got 1.09. And when we took natural log of 10, we were over 2, right? So the further out I went, the area got larger. Obviously, if I move to the left of 3, my area is going to get smaller, right? What happens if I do like 1.1? Right? So if I take natural log of 1.1, I get about 0.0953, which sort of makes sense, right? If I do 1.1 right here, the area under the curve is about 0.09, so it's tiny. So notice when I'm down here close to 1, my area is tiny. When I get to 3 or later, the area is bigger than 1. So somewhere between 1 and 3, there's a place, say, right here, where this area is exactly 1. Right? Because when I'm close to 1, the area is small. When I get to 3, the area is bigger than 1. So somewhere in there, at this point, the area under the curve is actually 1. So I want the natural log of something to be the area 1. So when does that occur? We call that number E. Okay? So E is a number. It stands for a number. And it's the place on the x-axis where the area under this curve, y is 1 over t, from 1 to E, that area turns out to be 1. Now please don't let E throw you. E is a number just like pi. Everybody knows pi is about no it's not. Pi is about 3.1415, 9265, right? Okay, so if I said on the number line 0, 1, 2, 3, 4, and I said, where's pi? Everybody would know to put it right about here. It's a little bit bigger than 3. Okay? It turns out E, the number E, is about 2.718281828. Now, what's bad is a lot of books will do this and they'll stop the decimal right there, but it makes it look like those 4 digits repeat, and it doesn't. They don't. It's 1828182846. The next 2 decimals are 46. So it doesn't repeat. So just like pi, E is irrational. The decimal goes on forever and it doesn't repeat. E is irrational. And so where's E on the number line? It's right about there. There's E. Okay? E is a number. In fact, why is it called E? Because it's named for the mathematician Euler. So that's why they use E. It's Euler's constant. Okay? So E is irrational. It's about 2.7. And what does E represent geometrically? It's the place on the x-axis where the area under the curve, y is 1 over t, from 1 to that place E, the area turns out to be 1. Okay, so that was plenty that we did, and we'll finish this section on Monday.